But by the time it gets down to you, it's not a liquid anymore. So now, that's kind of a cool effect, isn't it? Isn't that pretty cool?
Yeah.
So it's, you see how much water's in the air. You just see, just from that. Okay, so we put this nozzle on here because this nozzle's got a little porous metal piece, and it slows it down and it separates the phase. It's coming out of there because it's so cold, it wants to turn into a gas phase, but it still has some liquid phase to it. So as we turn this on, you can you see the rain that comes out of the rain?
Yeah.
So that liquid, so it's coming out as a liquid. Now we're specifying liquid nitrogen. So therefore it has to be, again, what condition?
Below
Negative 20 or 321 degrees below zero, or 196 Celsius. Yeah, and that's water vapor that's condensing. So we have water vapor all around us, and we're even breathing out water vapor. We breathe out carbon dioxide, we breathe out just as much water vapor. Okay, so I can condense my breath. You guys can probably condense your breath in the wintertime, right? So the same thing, it's water that's coming out. It's not, you're not smoking, you're water vapor. Okay? So it's, now, is this evaporating?
No.
Yes, it is. But it's evaporating very slowly.
Yes.
But if I take some nitrogen, which is cold, I'm not going to put it in the water. I'm going to put it in a cup, and the cup, see it, how it's condensing the water vapor, just like it's condensing my breath. It's condensing the water vapor that's evaporating. So now I can see it. Now I can see how much water is coming off of that, as it evaporates. I take it out, no nitrogen in there, but it's not, you can't see what's being evaporated. So I put this in here so I can cool it and cool just the part that's evaporating, and you can see how much is evaporating. Okay, so now if I want to have, why don't you come up here? We're just going to do this with one person. Okay, that's a liquid, right?
Yeah.
And so it's 300 degrees below zero, but I can touch it, right?
Should I touch it?
Well, real quickly, not very long. So does it make your hand wet?
Yeah. No, well,
No.
it feels wet when
Feels
it's
wet
in
when
it,
it's in there, but
when you take it out, it's not.
Right, and because it's not water, so it turns to a gas, and we call that the Ledienfrost effect. That's good. That's so that you can sit down. So the Ledienfrost effect says that if there's two things that are really different, or very different in temperature, then the liquid will vaporize, and then and create a gas barrier between those two things. So that's one of the things that protects us when we're using liquid nitrogen at low pressure, is the fact that it creates that Ledienfrost effect. Now they named it Ledienfrost not because it's frost, it's because the guy's name was Ledienfrost. He was a doctor, Dr. Ledienfrost. And so that discovered this. Now, so if you take your hand and make it wet and stick it into molten lead, it will vaporize the water around your hand, and it won't burn you, but you can't leave it in there. You have to pull it back out real fast. So but if you have a hot pan at home, and you take cold water and throw it on the pan, and it sizzles and levitates, right? Then that's the Ledienfrost effect. Same type of thing. So there's a video called hand versus liquid nitrogen, and it goes into more detail on that. So the next thing we're going to talk about is PvnrT, and so this is the ideal gas law. This is not the PvnrT that your parents warned you about. Huh? Well, Maybe if they took chemistry in college, they got freaked out about it. But anyway, it's the ideal gas law. This is the ideal gas law. The ideal gas law says that pressure times volume equals the number of moles. Am I getting you lost? The pressure times volume, you're not going to lose you, right? Equals the number of moles. Anybody know what a mole is? Anybody know what R is? R is a constant. And then T is temperature. So since these don't really matter to us for our purposes, we're just going to ignore those. We're going to go directly to a simplified ideal gas law, pervert. So PV equals T. So if I take a balloon that has a gas in it from my lungs, and what do I breathe out? We talked about this.
Carbon dioxide.
And
Water.
water vapor. What does carbon dioxide look like? What color is it when it's solid?
White.
White. What about water? White. Right. So if we take this, now again the red balloon is going to taint the color that we see through it. So we kind of have to filter out what we think the color is. So if we take this equation and we say pressure times volume equals temperature, and we drop the temperature, so temperature goes down, is pressure and volume going to go up or down? Down. Okay? So should we try that?
Yeah.
The balloon's going to go down, right? Low pressure, low volume. Okay, so
Poor balloon.
you have your phone. You mind roll out the light on it? You need to bring a flashlight. This should be all right.
Oh.
Okay.
Oh, especially with that one.
Huh? That's all right. We'll figure it out. So can you see a liquid in there? Can you see a shadow of a liquid in there?
Yeah.
Okay. So that liquid is the condensation.
What's the head?
You see that? There's a shadow in there of the liquid in the bottom. You can see it kind of rolling around now that it starts to expand.
Wow.
As it heats back up, it starts to expand.
So cool. That's
Okay?
the coolest.
So that's what condensation is. Now when liquids, when gases condense, they condense by 600 times. 600 times. So when this reinflates or evaporates inside there, okay, you see that? The liquid right inside the bottom. There should be a shadow you can see. And so then it expands by how much? 600 times. So if it thank you. So if it condenses by 600 times, it also expands by 600 times. Now where's the heat coming from that makes it? The air, right? Exactly. So the air we breathe has heat. Now, which is more dense? Water or the air? Water, right? Okay, so it's more dense, and therefore there's more molecules in water than there is in